time. I did not notice that. And if that's true, that's pretty interesting. Donald says, not really related, but slightly to the point, you didn't explain how GPS works on Mercatus stream. So I have to explain how GPS works now? Okay. All right, I'll explain how GPS works. I'll do the super chat, then I'll explain how GPS works. All right. Eagles Paws Gaming says, for $5, wasn't there a state of emergency declared for temporal charge as the legal structure of given jurisdictions the terms outlined by the states and statutes? Yeah. All right. So here's how GPS works. Okay. So all the GPS satellites have an atomic clock built in them, right? So these are the most accurate clocks that you can have, right? Atomic clocks, they keep the most accurate time, right? And so each of the GPS satellites is on a known orbit, right? So if it's satellite number 12, then you know what its orbit is around the Earth, right? And you know the altitude it's at, and you know the path that it takes, right? So this can be programmed into the GPS. So you program into the GPS, okay, satellite 12 is at this high. This is at this altitude, and it's on this path. So it's on this circle around the Earth, right? You plug that into the GPS device. Okay. So what the GPS receiver does, what the GPS satellites are doing constantly is broadcasting the time. All right, they broadcast the time. And what the GPS receiver does is it receives all the time. So the GPS receiver is basically asking constantly, what time is it? What time is it? What time is it? All right. Now, because the speed of light is not instantaneous, right? The speed of light takes time. Because the speed of light is not instantaneous, the answers that it gets from the GPS, even for the same satellite, won't be the same, because the satellite has moved, right? So if the satellite is directly above you, right, and the beam is coming directly down, that takes so long. But if the satellite is on the horizon and coming across this way, it's further away, right? So the time gets the answer to the time basically comes distorted by the amount of time it takes to travel. So let's say the GPS says it's exactly 12 o'clock. All right. So if the GPS says it's exactly 12 o'clock and you know it's exactly above you at exactly so much height, then you say, okay, given the speed of light, it says it's exactly 12 o'clock. But that's not correct, because I know how far above it is of me and I know how long that takes. So I can add the amount of time that I know it takes, because the position of the GPS is predictable. So it's not actually 12 o'clock. It's actually 12:00:00 point blah 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 blah, whatever, right? Okay. So it can do that, and it can do that for all the satellites, and it can do that because the satellites are on a predictable path. Okay, great. So then for each satellite, you're asking what time it is, and each satellite is telling you the time. So you know it has to be somewhere above you within the horizon, right? So it can only be part of the circle. So it can't be everywhere in the circle. It can only be part of the circle that's within your horizon. Because it's below the horizon, you can't hear the time anymore because it's below the horizon. All right. So now what you do is you get a number from this GPS. It says, okay, you say, all right, it's 12 o'clock. It's on a predictable path. So I know where this satellite is. So it's not really 12 o'clock. It's really this time, because I know where the GPS is. So I know that the GPS satellite is this distance away from me, but I don't know where it is away from this distance from me, right? If it's directly above me, it can only be directly above me because there's only one way. That's only one time, right? But if it's any other time, it's somewhere on a circle, right? Somewhere on a circle, because if it's off by 15 seconds, which is ridiculous. But if it's off by 15 seconds, then it could be anywhere on a circle above you, the distance to which is 15 seconds of deviation. So you're somewhere within that circle. And because the circle actually is a sphere, right? Because you're anywhere on the surface of the sphere, right? So you know that you're on the surface of a sphere that's so far away from the GPS satellite that's telling you what time it is. Okay, so now you know what sphere, now you know you're somewhere on the surface of the sphere. Great. So now what you do is you ask the other GPS satellites, what time is it? And now satellite number 15 comes along and says, oh, here's what time it is. I think it's 11:59, blah, blah, blah. And then satellite number 27 comes along and says, oh, I think it's 12:01 point blah, blah, blah. Or the satellite number 1 says, oh, I think it's, you know, blah, 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 whatever, right? So each of the satellites is telling you what time it is, and each of them are different, and each of them are wrong. They're all wrong because they all take time to get you, but they're all predictable. So now in the GPS receiver, you say, okay, I must be on the surface of a sphere that has this radius. So I know I'm somewhere on the sphere that has this radius, and I know I'm somewhere on the sphere that has of this thing that has this radius. So now you have intersecting spheres, right? So GPS satellite number 1 and GPS satellite number 2 are both telling you the time. You both know you're on the surface of the sphere. So you must be on a place where the two spheres intersect. Right? That's the only place you could be. You're all both on, you have to be on the surface of both spheres at the same time. So you're on a place where the spheres intersect. Okay, great. So then you ask a third satellite what time it is. And now you're up to 2 dimensions. So with 3 satellites, you can tell 2 dimensions. So you need a minimum of 4 satellites to tell you 3 dimensions. So with 4 satellites telling you 4 spheres, you can say, I'm on the surface of all these spheres and there's one intersection point and I must be exactly there. And that's how you know where you are. And then you use other GPS devices to further get even more accuracy. Because again, you're dealing with the time being slightly off, and the time can deviate slightly from atmospheric conditions and other factors, right? So you can't even be sure the GPS is exactly telling you the correct time for sure, because it could have changed somewhere along the way because of the atmosphere or something else, right? It could be reflected or whatever else. So now you ask a 5th satellite, and you ask a 6th satellite, and you ask a 7th satellite, as many satellites as you can get. You ask, what time is it? And all 7 satellites tell you what time it is. And then from all those times, you can generate the spheres of every satellite, and you know you're on the intersection point of all those satellites, and bingo bango, you have GPS. Now, what's even worse, now what's even more fun for the GPS is you have to deal with relativity, which is even more fun, right? So you know, or you should know, the closer to the speed of light you go, the more time itself slows down. Right? That's relativity. Time is not a constant. The faster you go, time itself slows. Time itself slows to the point where if you could go the speed of light, the time would stop. Relative to you, it would stop. If you could go the speed of light, which of course you can. But these satellites are in orbit, right? And the orbits are really, really fast. They're moving at like, I don't even know, 20,000 miles an hour. Which means that even though these GPS devices use the most accurate clocks known to man, you have to account for relativity because the clocks themselves are not ticking at consistent rates, because the GPS receivers are at different altitudes and they're moving at different speeds, which means that each clock is moving at a different rate of time. The time is not even consistent from satellite to satellite. And when you're talking about GPS and trying to get down to when you're trying to get down to smaller and smaller granules of location, you have to have more and more precise time. Right? Because if you're just like, what are your margins of error? So if you're to the nearest minute, and this is not even going to be close to accurate, but it illustrates the point. If you're to the nearest minute, maybe you can say you're within 10 degrees of latitude. If you're in the nearest second, you're within so many degrees of latitude. So the more precise you want the GPS to be, the more precise you need the time to be, which means that now you start having to account for relativity, because the clocks themselves, well, they're not exactly wrong, but they're all ticking independently because you have to now account for relativity on top of all of that. So that's how GPS works. GPS works by a very complicated method of asking what time it is and getting the answer. I hope this helped. The GPS doesn't ask what time it is. The satellites just call it what time it is. Yes, 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 that's true. They're not literally asking the satellite to tell them what time it is, because the receiver doesn't have the ability to communicate to the satellite. So yes, they're not literally making a call to say what time it is. I was using it more as a metaphorical of what time it is, let me look at my watch. Right, so I was using it as like, I want to know what time it is. Let me go look at my watch. Oh, the satellite says it's this time. I was implying consciousness to the GPS receiver, I guess. A couple things. We don't know correct local time at the start, so no longer predictable. So we have to solve simultaneously timed notion too. Well, we do have the ability to know for local time at the start. We do have the ability to know local time for the start, but of course you have to adjust it going the other way, because we do have the known time on Earth. And for the military, that is the National Observatory in Washington, D.C. For the civilians, it's the, I used to know this so well. It's a radio tower. It's NIST, National Institute of Standards and Technology. So yeah, for civilian applications, for civilian applications, the legally correct time is kept by the National Institute of Standards and Technology. They have a radio station in Colorado. It's called WWVA, and it broadcasts the time. And your watch or clock, if it's a radio-controlled clock, you ever see those clocks that say they're radio-controlled clock to know the time? Yeah, it's because the radio's in Colorado. It's called WWVA. It's controlled by the National Institute of Standards and Technology. You're welcome. For the military, it's controlled by the United States Naval Observatory, which is the home of the Vice President, and is Washington, D.C. So we do have a known local time because we have the NIST and USNO master clocks. So they can also correct the GPS's clocks, right? So if you want to correct the GPS's clocks, you can do that because you feed them the time from the USNO master clock. And of course you have to account for all the things I mentioned before, but you do know the local time because USNO master clock. Electromagnetic waves only propagate at the speed of light while in a vacuum. Makes calculations GPS way more fun. This is correct. This is correct. I failed to account for that in my explanation. You're absolutely correct, Vignectius. The speed of light itself is not constant because the speed of light changes as it passes through mediums. And depending on the medium, you can actually get to move pretty slowly. So yeah, you also have to account for the fact the speed of light changes as it moves through the atmosphere. So there's also that. That's true. If we do have a radio clock signal, that's also wrong as it takes time to reach us. Yes, but for the clocks that are being adjusted by the radio signal, none of them are precise enough for that distance to matter. But yes, it is true. Yeah, if you're setting your watch or your wall clock from the radio signal, the time delay in the radio signal propagating is not enough to worry about. We're not talking about that level of accuracy. We are talking about that level of accuracy with GPS because we need more accuracy for more precise location calculations with lower margins of error, which is very important. For example, if you want to use GPS to, for example, autopilot a car, probably very helpful to know exactly where it is, just as a suggestion. You can give a lecture about computer encryption. Oh, public key encryption. Oh, that's pretty fun because usually I go with the paint colors to explain how public key encryption works. I think it's a pretty classic to explain public key encryption. So yeah, well, you have two different kinds: asymmetric and symmetric encryption. So you have one key or you have two keys. And public key encryption, which is the internet, uses two keys. So we could talk about one key encryption. The most famous of which is probably what's it called? When you have a pad, when you have a completely random pad that's at least the same length as the message and it's completely random, and it's called I should know this one. Help me out. Yeah, it's a single key encryption. A single key encryption, it's just called a one-time pad? Yeah, it's just called a one-time pad. Okay, yeah. So I thought it was a more complicated name than that, but you're right. It's just called a one-time pad. For some reason, I got confused and thought it was a more complicated than that. Okay, so there's two different kinds where you have one key and you have two keys. So if you have one key, you need some method to get the key from the person who's encrypting the message to the person who decrypts the message, which means you need a secure channel. And if you already have a secure channel, then why are you bothering with the encryption in the first place, right? So one key encryption, but it does have some advantages, the most obvious of which is for one-time pad. So in one-time pad, you literally use one pad one time. You have to have a pad that's at least as long as the message. So you can't repeat the message. The pad has to be random. And you have to have a different pad for every message. So if you use a one-time pad, then it's unbreakable. It's unbreakable. And you can prove that mathematically. Because if it's truly random, then you can decrypt the message into any message of the same length, because because there's nothing to extract the pattern from. So if you have a known answer and it's known with a one-time pad, it's unbreakable, because the answer could literally be anything that would be that length. You have no way to determine what the correct message is from an incorrect message. There's no way to determine that. So it's mathematically perfect. Now, this is less a problem now, but in the early days of encryption, it was definitely a problem, where there were people selling software that they said used a one-time pad, which doesn't even make sense. It's like, how's that even possible? It's not, by the way. But you did have some snake oil people in the earlier days of encryption saying, well, we're doing like software with one-time pads. No, you're not. But, you know, one-time pads are the most secure. So it's been suggested that they're used for, like, you know, really secure nuclear missile encryption or something. I don't know about the degree to which that's true. All I can say about, you know, the nuclear message encryption is Skybird, do not reply. Skybird, do not reply, is all I can say about the nuclear message encryption. Great. Now, or I think it's do not answer, actually, instead of do not reply, but I was close. Anyways, where was I? Oh, yes. So then two key encryption, PGP being perhaps the most famous, or RSA, or any of those other things. Is randomness even possible? Sure. It's just, yeah, there's really good ways to generate randomness. Perhaps the most secure way to generate randomness is through using a nuclear decay. Because whether or not the decay will spin to the left or spin to the right is truly random. And we have no way to predict it given current theory. So yeah, if you want truly random numbers, the best way to do it is by looking at the spin of a decaying nuclear atom, which, given all knowledge we have, is random and there's no way to predict it. So yeah, you can generate true randomness. That'd be great. If you want something a little less secure, then random radio noise is fine. So just turn to a radio station. Just turn your radio to a station or turn your radio to a frequency where there's no broadcast, and you'll get what you call white noise. What you're really getting is atmospheric static, incidentally, and that's random too. So you can use atmospheric static. That's also really good. Of course, you can use it during any you can use it with any number of physical methodologies to generate true randomness. With a computer, not so much. Your best bet is for pseudo randomness. But if you use like the exact time as your key, then you can get pretty close to something approaching true randomness. Although if you knew the exact time, you can regenerate the pattern. So pseudo randomness is pretty good, but it's not a thing. So anyways, for public key encryption. So public key encryption, you have a public key and a private key. And the easiest way to, and so when you combine the public key and private key, you get a message that can only be decrypted with both of them, right? So you publish the public key, that's the whole point. You publish your public key and you hold it private, your private key. So anyone can encrypt a message to you with your private key and their private key, or your public key and their private key. You can use their private key to authenticate they sent it, and then you can use your public key or your private key to unencrypt your public key. And the easiest way I have to analogize how hard it is to do this is by looking at color, because color is a pretty good example. So a public key and a private key are kind of like two colors, and you can determine what the combination of those colors is very easily, but it's very hard to determine what the constituent colors are, right? So if I give you any two colors, and I say, what is the combination of these colors? It's really easy. You just mix the colors and you're like, that's the answer, right? Very easy. If I give you the mixed color and I ask you what are the constituent colors that formed it, extremely hard, particularly if I need to know very precisely very precisely what the constituent colors are, which is basically what you have in public key cryptography, right? So it's not just red plus blue equals purple and trying to figure out what constituent colors made up purple. It's like what constituent colors made up this exact shade of purple, and by exact we mean pretty exact. And trying to figure out what colors those are, it's basically impossible to backwards engineer, right? You can't figure it out mathematically. So it's very easy to figure out one way and basically impossible to figure out the other way. But if I have my private key, right? So if I have half the color, so if I have the half the color, which is my private key, and you encrypted it with using my public key, right? I have the other half of the color. So now I get this bizarro color, right? And I know what one of the colors is because I have the private key. So because I know what one of the colors is, I can extract out my color from the combined color, and now I have the color that you had, right? Which is a way to authenticate it. And that's how you get the message. Does any of that make any sense? And then we could talk about Alice and Bob, but we don't need to talk about Alice and Bob. So, all that good stuff. The mixing paints is different. It's it's a Diffie-Hellman key exchange. That too. Yes, that is an example. That's an example of a public key encryption. So that's an example of a Diffie-Hellman key exchange. Exactly correct. You're correct, sir. Very good.